Hey there, Seahawks. It's Miss Adams, and in this video, we're going to talk about confidence intervals for proportions. All right, so if the conditions are met, the distribution of a sample proportion, p hat, follows the model where it's normal, the mean is equal to p, the population proportion, the standard deviation is equal to the square root of p times 1 minus p over n. So this is going back to the last unit where we talked about sampling distributions. So, however, most of the time we don't know the population proportion p. So we take samples and calculate p hat in order to try to find p. Since we don't know p, we can't find the standard deviation. All right, so p hat is our estimate for p. We can estimate the standard deviation with something called standard error. So the standard error formula is very similar to the standard deviation formula, except instead of using p, I'm using p hat. All right, confidence intervals, the basics, based on p hat and the sampling distribution of p hat. So we start with p hat, and we give ourselves a margin of error on either sides. The size of the interval, the margin of error, is based on the sample size, n, and the level of confidence. Larger sample size are going to lead to smaller intervals, which will be more accurate. Larger confidence levels will lead to larger or wider intervals, which will leaves more room for error. All right, our basic setup for a confidence interval is our estimate plus or minus our margin of error gives us our interval from A to B. The specific formula for a one proportion sample is p hat, that would be our estimate, plus or minus z star times the standard error, which is the square root of p hat times 1 minus p hat over n. Both of those pieces in pink make up my margin of error, and that gives us our interval from A to B. Z star is the critical value, which we'll talk more about. All right, so the three main confidence levels, the three main Z stars, you're going to probably want to memorize these. You can find them on your reference sheet, like on the Z tables. You can also find them on your calculator. So 90 is 1.645, 95 is 1.960, 99 is 2.576. Those are the most common ones. It's going to be a little bit faster if you just know those. Other confidence levels. So how do we find Z star if it's not one of those that we're going to just have memorized? So let's find the confidence level is 92%. Let's figure out the Z star, the critical value. So I'm working with a normal distribution. 92% is in the middle there. Well, that would mean I have 8% remaining, so 4% on both tails. All right, this is a normal distribution with a mean of 0 and a standard deviation of 1. So a standardized normal curve, which is what we use for z-scores. All right, so in order to find z star, I would do an inverse norm. My area would be 0.04. I'm doing the area on the left side. Mean of 0, standard deviation of 1. I get 1.751. You actually probably get negative 1.751 because it's 1.751 standard deviations below the mean. But you can ignore it's just the absolute value of those. On some of the calculators, you have the option to do left, right, center when you do inverse norm. So if you want, you could also do 92%, so 0.92, 0 for the mean, 1 for the standard deviation, and then pick center. And you'll get both the positive and the negative one. It's just telling you how many standard deviations am I away from the mean in order to capture 92% in that interval, right? Alrighty, make sure if you're going to show work for finding Z star that you label your calculator notation pieces. Alright, the sentence we use for interpreting our interval. So we are blank % confident that the interval from blank to blank captures the true, whatever the parameter is in context. And there's a couple other ways we could state this. So we're going to have these stock sentences and we're going to reuse them. Alright, so kind of find what works for you and then reuse it every time, just plugging in the appropriate numbers in the context. The conditions that we're checking are randomization, the 10% condition where the population has to be greater than 10 times my sample, or n has to be less than 1/10 of my population, and then my normal condition or large counts, n times p has to be greater than or equal to 10, and n times 1 minus p has to be greater than or equal to 10. All right, so randomization is for estimating the mean. The 10% condition is for finding our sampling standard deviation and large counts is so that the shape will be approximately normal. I'll have at least 10 successes and at least 10 failures. If all the conditions are met, then we say p hat has a normal model with a mean of p and a standard deviation of the square root of p hat times 1 minus p hat over n. And we can use a normal model for a 1 proportion C interval. All right, so what does whatever percent confidence mean? So if we're asked to interpret the confidence level, this is a little bit different than interpreting the confidence interval, in whatever the percent of all possible samples, the interval captured from the sample data will capture the true whatever in context, the true proportion of pigs that can fly, whatever it is. All right, so the 4-step process that we're going to follow is state, plan, do, conclude. So for all inference procedures, we will use this process to show all work and get the max amount of points possible on the AP exam. Context is extremely important. In addition to checking the conditions, you really need to understand the why. So the random condition, so that we can generalize to the population. The 10% condition, so sampling without replacement is okay. And then large counts, so the sample distribution of the sample proportions will be approximately normal, and we can use Z star to calculate. All right, let's do an example. We want to know the real improvement rate for a new medication. We conduct an experiment and find that out of 53 subjects, 27% of them report improvement with the new medication. Create a 95% confidence interval and interpret. All right, so we're going to do state, plan, do, conclude. For state, I'm going to define my parameter. So P, I'm working with proportions. P is the true proportion of improvement with the new medication. My confidence level is 95%. I'm also going to go ahead and say N, my sample size is 53, and P hat, my sample proportion is 0.27. Make sure when you're defining the parameter, you're stating it as P, because it is not P hat. It's the true proportion, so what we're trying to estimate with our sample proportion. Plan is where I'm going to check my conditions, so random, assume the sample is representative of the population. They didn't say it was random, so that's going to be my sentence for when it's not stated. The 10% condition, my sample size was 53. 53 is less than 1/10 of all subjects taking the medicine. And option 3 is our normal or our large count condition. 53 times 0.27, that's N times P hat, gives me 14.31. And then 53 times 0.73, this 0.73 came from 1 minus 0.27, is 38.69. Those are both greater than or equal to 10, so that condition is met. All right, now we can move on to the do. Because my conditions are met, I'm going to do a 1 proportion C interval. So my interval is my estimate plus or minus Z star times the square root of P hat times 1 minus P hat over N. P hat is 0.27. Z star for a 95% confidence interval is 1.96. I'm going to plug all these pieces in. So again, P hat was 0.27. 1 minus 0.27 is 0.73. N was 53. So when I plug all of those into my calculator, I get 0.1505 to 0.3895. So now I can write my conclusion. So we are 95% confident that the interval from 15.05% to 38.95% captures the true proportion of improvement with the new medication. All right. We take a simple random sample of 95 Pasco County residents and find that only 20 of them approve of the new property tax to pay for repairs to local roads. Estimate with 99% confidence the true percent of people who approve the tax. All right, so we're going to follow state, plan, do, conclude. For state, we're going to define our parameter. So P is the true proportion of people who approve the tax. When possible, I like to pull it directly from the question statement that they gave us, their wording. The confidence level was 99%. P hat, my sample proportion, would be 20 out of 95, which is 0.21-ish. N is 95, my sample size. My conditions, random. They stated that it was from a simple random sample. I like to put that in quotation marks, how they worded it. 10% condition, my sample size was 95. 95 is less than 1/10 of all Pasco residents. And then the normal or large counts condition, 95 times 0.21, that's n times p hat. And then 95 times 1 minus p hat gives me values that are both greater than 10. So on to the do. My conditions are met. I can do a 1 proportion z interval. My formula for that is p hat plus or minus z star times the square root of p hat times 1 minus p hat over n. P hat is 0.21. Z star for 99% is 2.576. And I'm going to plug in p hat, 1 minus p hat, and n. When I plug all of this into my calculator, I get 0.1024 to 0.3176. And for our conclusion, we would say we are 99% confident that the interval from 10.24% to 31.67% captures the true proportion of people who approve the tax. All right, so some more about margin of error. Things that affect the margin of error, or MOE, are sample size and the confidence level. If we want a particular margin of error, we can set the level of confidence and the sample size in order to obtain that margin of error. All right, so the formula for finding margin of error is z star times the square root of p hat times 1 minus p hat over n. Okay, so it's your critical value times your standard error. All right, so let's go back to our example about improvement rates with a new medication. We found 27% improvement. How many subjects would we need in a new experiment to make a 98% confidence interval while still keeping a 5% margin of error? Okay, so if I know I want the margin of error to be 5%, the confidence level to be 98%, I want to know what is the sample size that I need. Okay, so I'm going to fill in the pieces here. The margin of error needs to be 5%, so 0.05. Z star at 98%, okay, I would have to use my calculator to an inverse norm or use a table to find that Z star for 98%. I know that p hat is 0.27 and 1 minus p hat is 0.73. I don't know n. So now I'm going to do some algebra to solve for that n. All right, I'm going to show you all the steps just because we don't do algebra that much in this class, in case you've forgotten. So I'm going to first get rid of the 2.326 by dividing it on both sides. And I'm going to simplify. 0.27 times 0.73 gave me 0.1971. So I did that under the square root, and then I divided 0.05 by 2.326. Now I don't want the square root, so I'm going to square both sides. That'll cancel out the square root. When I square 0.0215, I get 0.0004623. Then I have n in the denominator, so I want to multiply by n to get it out of the denominator. And then I have n on the other side. I want to get n by itself, so I'm going to divide by the thing attached to n on both sides, and I get n equals 426.3. And because we're talking about subjects, number of people, I need to round that up. Even though 426.3 wouldn't necessarily round up, if I have 0.3 of anything and then we're talking about people, I need to round it up. I need at least 427 subjects for this to work. All right, if you are not given the value for p hat, then you're going to use 0.5 or 50%, okay? That's going to be the most conservative measure. It's going to give you maybe a little bit larger of a sample size, but it'll make sure that your margin of error still works. So what sample size must be used to estimate the outcome of a political election if a margin of error of 3% and a 99% confidence? So I know the margin of error I want and the confidence level I want. They didn't give me the sample proportion, so I'm going to assume p hat, 50%, and then I'm going to try to solve for n. So the margin of error was 3%, so 0.03. Z star at 99% is 2.576. For p hat, I'm doing 0.5. 1 minus 0.5 would also be 0.5. And then I'm going to solve for n. You should get 1,844 people. All right. What sample size must be used to estimate the true percent of left-handed people in the nation with 90% confidence and a margin of error of 8%? Assume that it has been shown in previous research that the percent of left-handed people is 38%. Okay, so see if you could try this one. All right, so they said the margin of error needs to be 8%, so 0.08. Z star for 90% is 1.645. They gave us a sample proportion of 0.38. 1 minus 0.38 is 0.62. I don't know n. So again, if you didn't try it, go ahead and see if you can try and solve for n here. All right, you should get 100 people. All right, go Seahawks.